Okay, we also talked about the character of sound, how it's built, how it's described, what it really means. We talked about diffraction, how sound can go from one medium to another and refract, just like light does. We talked about reflection. We talked about sound radiates from a sound source, small sound source. It'll radiate not in a straight line, but in a spherical way. But it all depends on how close you are to the sound source. If I'm standing right in front of a speaker, it appears as if it's a plane of sound hitting me. If I'm standing far away, then I know it's a sphere of sound. And that's why when you're listening to music, you can walk behind the speakers and still hear the sound too. But the interesting thing is, you hear less high frequencies when you're behind the speaker, because high frequencies are more directional than low frequencies for our hearing. We talked about that. We talked about directionality. And how did we talk about directionality? We talked about the fact that if you've got your two ears, and a sound source is over here, right? So it's radiating spherically, right? And it gets to this ear before it gets to this ear because distance A is shorter than distance B by the width of your head. That means the sound is going to be in different places in terms of its phase. So your brain then can calculate, oh, it's coming from over there. That's directionality. And it's really important. The one thing that I thought was humorous that I realized is that when the frequencies go down low enough, then because they're so long, 40 cycles is like 28 feet long, the distance between your ears is really insignificant. So the phase difference of the sound wave is really relatively nothing. And so your brain can't calculate where it's coming from. So we lose our directionality as you go lower than 200 hertz. You start losing directionality and being able to determine what direction a sound is coming from. But if your head's really wide, 10 feet wide like an elephant, then you can hear directionality way down, very low frequencies. So directionality is a really important part of this because when we listen to stereo sound, it's all about directionality and where the sounds actually emanate from in terms of where your brain can locate them. And that creates sonic space for a mix. You've got left, right, you've got front and back, and you've got sort of a space like a canvas to use to create your sound, your sonic picture. We also talked about the human hearing, being able to, the average human ear or human hearing can hear down to 20 hertz and up to 20,000 hertz. At least that's what we're supposed to be able to hear. As you get older, you start losing that range in your high frequency. But typically that's what we call the human hearing range, is 20 hertz to 20,000 hertz. Hertz is the same as cycles per second. We talked about the ear specifically and how it works. Let me draw a crude representation of an ear. 3 different parts, basically. You've got the outer ear, which everyone thinks it's just what you can see on the outside of your head. It's actually the ear canal all the way to the eardrum. The middle ear is the 3 bones that actually impedance match the energy of acoustic sound to go into the cochlea, which is filled with liquid. Sound takes more energy to travel in liquid, so it has to adapt the amount of energy that's traveling in air that's moving your eardrum, and it does that with the bone structure, right? So that's your middle ear. And then inner ear. Okay, your inner ear is the cochlea, and that's where the sound excites hairs in this sort of snail-like structure that actually have nerve endings that go to your brain. 30,000 nerve endings from each ear going to different parts of your brain. So your cochlea actually, because of how it works, that low energies are excited more in the first part of the cochlea that's more closely related to the area where the bone structure is. And the low frequencies are really way curled in to the cochlea. It takes more energy to get into them, which ties into the picture that low frequencies are more energetic, have more energy. High frequencies have less energy. It takes more energy to excite the liquid in the cochlea all the way inside the cochlea. This is sort of a physical structure that breaks a complex sound into different frequencies, just like our frequency domain picture. It's pretty cool, right? Our ear is a spectrum analyzer and analyzes what frequencies are in the sounds we're hearing. And then it sends it to different parts of our brain. That's why you may prefer different types of music. Some with more low end, some with more high end. It all depends on, what part of your brain you're exciting differently. And it also leads to the fact that that's why people's moods get affected by music. It's not just what the lyricist is saying, it's also the sound of the music itself. We're talking about the Fletcher-Munson curve. The Fletcher-Munson curve is a representation of equal loudness. If I was to take a sound and scan frequencies from low to high, all at the same amplitude, or actually at different amplitudes, your perception of equal amplitude, how you perceive what the same volume of each frequency is. So if you were to say to somebody, okay, at that frequency, that's that loud. Go to the next frequency. Oh, turn it up, turn it down. Oh, that's what I think is about the same loudness. And then go to the next frequency. Turn it up, turn it down. You tell them how loud to make it sound as if it's the same amplitude. And the Fletcher-Munson curve is related to how a human would perceive equal volumes from different frequencies. And then on the curve, it gives different amplitudes, getting louder and louder and louder. And as it gets louder, this curve gets flatter and flatter and flatter. But as it gets louder and louder and louder, more energy gets into the eardrum, gets into the cochlea. You hear the low frequencies better, you hear the high frequencies better. That's why music louder sounds better. I think it's sort of a given that everybody agrees that when you hear music louder on your headphones, it sounds better. It's because you hear more definition. You hear more of the upper harmonics that you weren't hearing before because they were too quiet. And so the upper harmonics give you the quality of the sound. So the vocalist sounds more lifelike. The violins sound more real. And you also hear more low frequency, and it's a more balanced frequency response. So the whole point of putting the Fletcher-Munson curves in the cards, the reason that I put it in there is to remind everybody that your ear itself has a frequency response, and it's not just flat. So what I'm hearing may not be what you're hearing exactly. It's like sight. My eyesight may be different than your eyesight. So when we look at the same picture, we may see it slightly differently. And that actually boils into when I'm mixing something that hopefully millions of people are going to hear, it's very hard to judge exactly how they're going to hear it. So I can really only go by what I feel sounds good and hope that other people hear it the same way.